I'll really be impressed if you can remember from last year who L'Hopital stole the rule from, and it actually should be named after. Because I did tell you that last year. Do you? Anybody remember? No, not from Leibniz. That was Leibniz and Newton had a little thing. Nope. Okay. So this is Bernoulli.
Is his first name you?
Yes, John. Okay, John Bernoulli. All right, John Bernoulli was actually the one who had this rule, and then L'Hopital quoted the rule in his book and gave credit. Said this is, John Bernoulli came up with this way to deal with indeterminate forms, and he did quote him. The problem is that L'Hopital's book was the one that got published over and over and over. People just kind of kept calling it L'Hopital's rule because it was in L'Hopital's book, even though it was John Bernoulli's rule. So everybody knows it today as L'Hopital's rule. So bummer. All right, so L'Hopital's rule, aka Bernoulli's rule, this allows us to find the limit of indeterminate forms. All right, so of functions in indeterminate forms. Trung, did you, hang on one second, Aubrey. Did you talk about this in your summer class? Or yeah? Okay. Yes, Aubrey.
I just want to ask you, what's the difference between an indeterminate form and then undefined?
Very good. That's what we're going to talk about. Okay. All right. So where can 0 be in a denominator? So we can have 0 in the numerator over a constant, 0 over k. Okay, so when 0 is divided by something, what's the answer? 0. Okay, that is defined. What if we have k divided by 0? What do we get then? Okay, we get infinity, which is undefined. And so then that leaves us with the only other result, which would be 0 divided by 0 itself. That is what we call indeterminate.
Usually I get it, but then sometimes there's certain ones where I think that it's going to be
So that's the difference. It all has to do with where 0 is and what 0 is being divided by. Now there are other indeterminate forms as well. Does anybody remember any from last year or whatever? Say that again. Okay, infinity divided by infinity is also indeterminate. Okay, does anybody have another one? Infinity minus infinity. Okay, so these are things where the elementary school rule that they tell you doesn't work anymore. Because they say anything divided by itself is 1. Not infinity divided by infinity, and not 0 divided by 0. Or they say anything subtracted by itself is 0. Not infinity minus infinity. Okay, because there are different degrees of infinity. You can subtract infinity from infinity and still have infinity left, which is kind of bizarre. It sort of boggles the mind. Okay, another one. Infinity times 0. Again, the elementary school rule is if you multiply 0 by anything, you get 0. Not infinity. And then the final one that we're going to talk about is, oops, I don't know why I put an equal sign. Are we going to talk about any more? No, I think that'll be it. So these are also indeterminate. And L'Hopital allows us to work with all of them. So the rule says if the limit lim h approaches k, or c, let's call c a constant, of any f divided by any g, if that limit is an indeterminate form of any kind, so if you get an indeterminate form, then you can apply Bernoulli/L'Hopital, which says take the same limit of the ratio of the derivatives, so f prime over g prime. It's what we want the quotient rule to be, but it's really not. We'd love it if the quotient rule was this, but it's not. Whoops, then. And you keep doing that. If that turns out to be indeterminate, do it again. If it turns out to be indeterminate, do it again and again until you get a form that's not indeterminate. So we're just going to practice that today. A couple of different things. In order to be able to legitimately use L'Hopital, though, you have to show that it's indeterminate. If you just jump into L'Hopital without showing it was indeterminate, you're going to lose points. So you have to show that L'Hopital was warranted, that you are allowed to use it. So make sure that you check for the indeterminate value before just jumping in. All right, so here's our first example. So we're going to take the limit as x approaches 0 of the function 3x minus sine of x over x. So clearly, we can drop 0 into that, and we'll have 3 times 0 minus sine of 0 divided by 0. That's 0 minus 0 over 0. So we've shown that it's indeterminate by getting 0 over 0. So we can now apply L'Hopital. It's helpful to somebody like an AP person if they know that you're going to apply L'Hopital's rule. So sometimes it helps to write in the margin, I'm using L'Hopital or something. It's just helpful. And so then we're going to take the derivative. So derivative of 3x is 3, derivative of sine is cosine, the derivative of x is 1. And then we can plug 0 into that, so we'll have 3 minus the cosine of 0 over 1, which is 3 minus 1, which is 2. And so this limit value was 2. Okay. So we might be asked to evaluate the limit as x approaches 0 of x minus sine x, so something similar, this time over x squared. So once again, we check for the value of the original limit, so it'll be 0 minus the sine of 0 over 0 squared, which is 0 over 0. So again, it is shown to be indeterminate, so we will apply L'Hopital's rule. And L'Hopital gives us 1 minus cosine over 2x. So that gives me 1 minus the cosine of 0 over 2 times 0. That's 1 minus 1 over 0, and I get 0 over 0 again. So the first round of L'Hopital wasn't enough, and so you're going to have to apply L'Hopital a second time. So the limit approaching 0 this time, the derivative of negative cosine is positive sine over the value of 2. And now I can put 0 in, and I get 0 over a constant, which is 0, not indeterminate. Okay, any questions on that one so far? Okay. So let's do the limit as x approaches 1 of the quantity 1 over the natural log of x minus 1 over x minus 1. By direct substitution, we get 1 over ln 1 minus 1 over 1 minus 1. That's 1 over 0 minus 1 over 0, which is infinity minus infinity. So here's a different kind of indeterminate form. So I'm going to need to apply the L'Hopital's rule. The thing about L'Hopital's rule, though, is it can't apply to a subtraction problem. You first have to get common denominators before you can use L'Hopital's rule. And so the fact that you've got the 1 minus natural log of x, or 1 over natural log of x minus 1 over x minus 1 means you need to get a common denominator first. And so first we're going to have x minus 1 over x minus 1 ln x. So I'm getting a common denominator here. And then minus ln x over x minus 1 ln x. And then putting them together in the form of common denominator, because L'Hopital doesn't apply. So x minus 1 minus ln x over the product x minus 1 ln x. L'Hopital does not apply unless you have a numerator and a single numerator and a single denominator. Has to be expressed in the function f over the function g. So if it's not, then make sure that you do the algebra. So now I can go ahead and show that I'm going to need L'Hopital one more time. So I'll plug 1 in here. That'll give me 1 minus ln x, minus ln 1, over 1 minus 1 times ln 1. And that gives me 0 minus 0 over 0 times 0, so 0 over 0. So I have my indeterminate form again. So the indeterminate form has to be rewritten into the points where it's 0 over 0. Then I can apply L'Hopital's rule. Now I can do, and it gets a little bit ugly, but it'll be all right. We got to take the derivative of the numerator and the derivative of the denominator. Boy, can you do the derivative of the numerator for me? Yeah, 1 minus 1 over x. Okay, Trung, how am I going to do the denominator? Yep, you want to do it? Okay. Plus
1 times ln x.
All right. Now we'll plug 1 into all of that. So I'm going to get 1 minus 1 over 0 times 1 plus 1 times ln 1. So all of that, I get 0 over 0 again. So I'm going to need to apply L'Hopital's rule again. I'm going to suggest before you apply L'Hopital's rule that you simplify. I'm going to circle what Trung did, that section right there, Trung. Can you distribute and simplify that so it's a little bit easier for us to take a derivative of?
1 minus.
Yeah. So let's write that 1 minus 1 over x plus ln x. Okay, it's going to be easier for us in the long run if we're taking our derivative of that form. All right, Tom, can you do the derivative of the numerator?
Wait, so the top part
Mm-hmm.
should be 1 minus.
Not 1 minus. What's
1
the derivative?
plus,
No.
1 plus
No. There's no 1.
Oh, on the 1.
Yeah, there's no 1.
1 over x.
Okay, 1 over x squared. All right, Aubrey, can you do the bottom part? All right, so in yellow, the derivative of the yellow.
It's x. Sorry, it's can't like read where you're at.
Yep, so we're ready to take the derivative of what's written in yellow, so the derivative of the denominator.
Oh, okay. It's 1 over x squared
Good?
plus 1 over x.
Okay, now we're gonna plug 1 into that. So I'm gonna get 1 over 1 squared, 1 over 1 squared again, plus 1 over 1. Whoops. Didn't mean to write that. 1 over 1 squared. All right, so we are at 1 over 1 plus 1. So my answer finally, after all of that, is 1/2. Alrighty, last one. Phew. The limit as x approaches infinity of 1 plus 1 over x to the x. Now this is a super exponential. So before we can do L'Hopital, what do we have to do like we did with other super exponentials?
Prove it's indeterminate.
Before we can even do that. When you have a variable in both the parentheses and a variable in the power. We just took a test on it. We're going to have to apply a logarithm. When you have a super exponential, where you have x both in the denominator or in the base and in the power, you're going to have to apply a logarithm on both sides.
Well, I was just saying to prove it's indeterminate first.
You can't. We're going to have to do our,
Prove it's indeterminate?
well, we're going to get 0 to the infinity, which I guess is it's not one of the ones we talked about, but it is an indeterminate form. So we are going to apply our logarithm first and then prove it's indeterminate. So when I apply a logarithm, I now am going to have the limit as x approaches infinity of x in front of the ln of 1 plus 1 over x. So now I've used a logarithm to help me pull x to the front. Now I can plug infinity in. So I'm going to get infinity times the natural log of 1 plus 1 over infinity. That's infinity times the natural log of 1, which is infinity times 0. That's my indeterminate form, infinity times 0. I think if you just did the tried to plug infinity in the first time, you would have gotten 1 to the infinity, which is not an indeterminate form. So this is your indeterminate form. So now we can apply L'Hopital. But remember, what form does the equation have to be in order to be L'Hopital? No, but the equation itself. I have to have a numerator and I have to have a denominator. So I got to think of a way to rewrite this. Instead of writing it as a product, that I can write it as a numerator over a denominator. So of the stuff in the product, right now I'm going to put it in yellow brackets. What should we leave? What do you think would be easiest to leave in the numerator?
Natural.
Yeah, let's leave that thing in the numerator. The natural log of 1 plus 1 over x. So then what do we put in the denominator to make sure this is still actually the same thing?
1 over x.
Yep. Now that it's in the form that we need, now we can apply L'Hopital because we have a separate numerator from denominator. So the numerator is going to have the derivative 1 over 1 plus 1 over x times Tom's favorite chain rule, negative 1 over x squared. The denominator is also going to have negative 1 over x squared. So conveniently for us, the negative 1 over x squareds are going to reduce. So we are left with the limit as x approaches infinity of 1 over 1 plus x. 1 over 1 plus 1 over x, excuse me. So that's 1 over 1 plus 1 over infinity, which is 1 over 1 plus 0, which is 1. And if you're working on a multiple choice problem, don't pick 1 as your answer. Why is 1 actually not the answer? Okay, because I used a natural log to get this whole problem started. So in order to undo the natural log that I used at the beginning, my limit is going to be e to the 1, or e, because you have to use the natural log to get back, use the exponential to undo the natural log that you had done. So the value of the answer is 1, but the value of the limit is e to the first.